Okay, so today is a video experiment, the first in a new series which I've called the Wheelwork of Nature. That is, for me, based on a quotation by Nikola Tesla, part of which goes, "It is a mere question of time when men will succeed in attaching their machinery to the very wheelwork of nature." And that, I think, has, that statement and understanding that statement has great import for how we learn to build our apparatus, how we learn to see the principles and the mechanisms that are reflected in our experiment as part of the natural world. Not only of the world that's outside of us, but also that inner world. So there is a bridge to be built there between the philosophical and the esoteric and the scientific. And part of my sequence on the wheelwork of nature is dedicated towards looking at the correspondences and the parallels between those fields. I think inevitably, sooner or later, when one is researching something like electricity, where you're looking for underlying principles, you're looking for life's hidden secrets, and you are looking for mechanisms and principles and how that all works, inevitably you will reach a stage where these questions are very loud and need to start to be answered. There's obviously a lot that one could say about this subject, and I am going to say a bit more about how I see it in the write-up on this experiment. But the Wheelwork of Nature, for me, the Wheelwork of Nature series, that I'm going to do a number of video experiments, is intended to look at how apparatus and experiments reflect some of those important properties and principles in the natural world. For example, like fractals, like the golden ratio, and many of those things which can help us to learn how to do what Tesla was expressing there, how to attach our apparatus to the wheelwork of nature, how to become in tune with the natural world. And it is very much an essence of tuning to the natural world, and the kind of phenomena and the kind of mechanisms and principles that we can uncover that will then obviously allow us to not only become more in tune and in sync with not only the surrounding world but ourselves, but also to be able to, as a result of being in tune, become a natural part of that flow in terms of energy, harnessing and using energy in a regenerative and efficient and effective natural way. I think, again, there's a lot that one can say in this area. I'm going to say some more in the write-up. So this first experiment, we're going to have a look at unusual phenomena that was, from my understanding, first demonstrated by Eric Dollard back in the 90s with his integrotron, and it led to that very famous Discharge picture, which also appears on the front page of Peter Lindemann's book, which shows the fractal fern discharge at the emitted from the top end or the hot end of the Tesla coil, extra coil that Eric was using in that experiment. Now, since that time, I mean, there's little, there appears to be little public knowledge or information about the details of that experiment and how to go about setting up that kind of experiment, the equipment needed, the conditions, and ultimately a video, an analysis and measurement of that discharge itself. And also looking for naturally occurring properties and principles within that discharge. So, as I said before, things like fractal-like nature, aspects and elements of the geometry which are related to the golden ratio. The natural unipolar forward pressure required from the power supply in order to be able to generate those kinds of discharges. So we're going to have a look at how to do all of that. So the equipment that we're going to use for this, this is the tube supply, plate supply. This is another series that I've been doing on the website. I already did the tube supply heater grid and screen supply. I'll just pan round. That supply is there with the Quad 811A board on top. There will be a write-up on the tube plate supply itself. I've made the video for that already, but I've not had a chance to write it up yet. So in this experiment we're going to use it. I'm not going to go into a great deal of detail about how it's constructed and what it does, other than here that it's a very versatile, high power, high tension supply which can operate in the region of between 2 kilovolts at 2.5 amps up to about 15 kilovolts at 200 milliamps, depending on how you arrange it, how many transformers you use and how you set it up. I will go into all of that detail when I talk about the plate supply, but that is the supply that we're going to be using to provide the high tension for this experiment. Now the coil unit, that's this system over here. This is what we're going to actually be doing to use the discharge. I mean, I've got a generic coil system, so this is a coil system that I use for this kinds of discharges, discharge or Tesla coil experiments, with quite a conventional Tesla coil on top with a primary and a secondary, but arranged to resonate at high frequency. This is about a 3.2 megacycle secondary coil. I'll go into detail about this. Obviously there will be the circuit diagram for this system and the write-up and the various pictures and all that kind of thing. I'll put a lot of detail in there. So this is the coil that we're going to be using. It's the primary coil and with a secondary. It's driven by a vacuum tube, GU5B. That's a nice peak power, 3.5 kilowatt peak power, Russian power triode, CW continuous 2.5 kilowatt, very robust tube, and also can operate up to some very, very high voltages. Though the plate supply is rated to about 5 kilowatts. 5 kilovolts. The in a pulse mode, it can take quite a lot more than that. You can easily push it up to around about 8 kilovolts if you're using it in a pulsed manner. We're going to be using it CW, and I'm going to go through how we set this up. So that's the high tension supply. Here, the coil unit, I've put a black board area behind, so we'll be able to see the discharge more clearly. So what I'm going to do is I'm going to move the camera in a little bit closer, and we'll just have a look at the various aspects of how the system is set up, and the more details of the coil unit itself. Okay, so I've moved the camera in a bit closer to the coil unit. The base unit basically is everything necessary to drive the GU5B triode. Basically there's a variac, there's a power on off variac which controls a 400 VA toroidal 12 volt transformer, which drives the heater in this. The heater in this nominally is 12.6 volts at around about 23-24 amps, although the tolerance is quite wide. It can go from 20 to 29. So the way that I adjust this, obviously I can adjust this very accurately by adjusting here, and I've got AC voltage and AC current on analog meters, so I can set that quite accurately, and I can adjust it around a little bit more or a little bit less, depending on how I want to drive it. The GU5 is built into a cooling tube here. This is a transparent perspex tube, which has got a mount at the bottom. When I take some pictures, I will take some pictures of the lower part of this through the side, so one can see how it's actually mounted in there. But at the bottom of that is a fan. So basically there is a laminar cooling airflow constantly coming through the tube up through the anode and the heatsink at the top here, and that runs continuously when the unit is on. Other things in here, so basically that's the heater side. There is on the side here grid control. We just check one can see that. Yep. So there's a grid bias control there. This system is being used as an Armstrong oscillator. So there is a feedback coil. Straighten it up again. So there's a feedback coil under here. Let me just see if you can see that. Yes. Underneath. So this coil will remove because I also use other coils on this system, and that leaves the feedback coil underneath. The wires come out the centre, down, and the feedback bias can be adjusted there's quite a large rheostat there, 150 watt, 1 kilo ohm rheostat, and that obviously allows grid bias to be adjusted to the GU5B. So under the two rows of terminals here, the positive terminals and the negative terminals, there is a copper bus bar, so they are all connected together, and that allows for easy changing of the coil system and the attachment of the various items like variable capacitors and static resonant capacitors, those kinds of things. So the anode comes down to here, connected here by very chunky wires. We've got a vacuum variable capacitor. I'm just going to turn around so we can see. Yeah, we can just see that inside here below the coil. That's a 10 kilovolt Russian KP14, 10 kilovolts, 20 to 1000 picofarad. That's a powerful variable capacitor, and that's used directly to tune the primary of the Tesla coil for best match with the secondary in the way that we've got it configured. Obviously, high tension comes in from the power supply, the capacitor and the primary coil connected in parallel. The output comes down to the anode, and then the cathode is connected down to the heater and also down to the earth of the line supply. So in this unit there is a external RF ground that I can connect to, but in this experiment I've just got it connected to the earth of the line supply. Same with the power supply. So basically the line supply earth is acting as the earth in this experiment. I wanted to keep it like that, so and not make too many variations by connecting the Tesla coil to RF ground, the power supply to the line supply earth, so that we can keep the configuration set up as straightforward and simple as possible. Then it's easier to not become confused about the conditions under which one is able to generate the interesting phenomena. So the overall, if I just turn the coil unit round, see the back, really it's just got a power supply input and the coil ground and the earth line supply ground are connected, and that also just connects the bottom end of the secondary coil. So very versatile unit. The performance of the GU5P is excellent, especially when you push it up to higher anode potentials, which we're going to be doing in this case. So on the right up I'll put some more detailed photos so you can see how this is constructed. Let me just turn this around again. Alright, so just check that's in the right position. Okay, so looking at the coil now, if we move up to the coil. Okay, so as I said before, this is a conventional Tesla coil. In its very simplest case, it's a primary coil, 7.5 turns there of silicone coated wire. That's AWG14. I'll put the exact information on the write up, and then similar silicone covered wire wound tightly in an aspect ratio of about 5:1. Now the reason I'm using a conventional coil wound like this is because I want to get lots of voltage magnification. So in other words, with a tightly wound secondary like this, with a close primary driven with a tube, I can easily get quite a large discharge. Now in this experiment it's not about maximising the length of the discharge. We're going to be looking at the geometry and the structure of the discharge. Obviously one can optimise for length of arc there, and then we'd be very concerned about making sure that all of the wires between the power supply and the tube coil unit as large and short as possible, that we're getting the optimum out of the power supply and all of those other things if one is trying to generate very large streamers. In this case we're more interested in the, as I said, the geometry and structure of the discharge, so that affords us some flexibility also to how we set it up. At the top end of the coil, so this is about 155 turns of this is equivalent to it's a 1mm squared stranded silicone coated cable. Again, I'll put the details of that in the write up, and that feeds out to a high voltage pillar with a convenient 4mm banana connector at the top, so I can connect various things onto the top, and the coil doesn't go inside the tube, so it stays on the outside. This is actually, when I measured this, I'm going to put the small signal AC analysis with the vector network analyzer, what I normally do with the coils, Z11, and then we'll see that the free resonant series, fundamental series resonant frequency is around about 3.25 megacycles, with no extension on the top. So with the bottom of the secondary coil earth series fed with the vector network analyzer, so not involving the primary, its free series resonant frequency is, as I said, about 3.2 to 3.25 megacycles. Now we are running this in the series fed mode with the tube, nice and convenient. It's easy to do. The feedback, creating a feedback oscillator there, an Armstrong Class C Armstrong oscillator, essentially, that forms with the feedback here, means that we are resonating it not at the series mode but the parallel mode. So every Tesla coil has a parallel mode to it. When you add a primary and you have tuned that primary to be close to the parallel mode of the secondary, then you get frequency splitting, and you get an upper and lower parallel resonant frequency. The parallel mode has a higher impedance, say typically around about 10 to 20 kiloohms, which makes it ideal to be powered in series with a vacuum tube. The anode resistance at resonance of the tube will be somewhere in the region of between 2 and 8 to 10 kiloohms, depending on the type of tube, and that makes it very compatible as a very straightforward match without making the circuit more complicated. Obviously you can drive it at the series fundamental mode. You need to drive the tube directly with a power oscillator, or in push-pull mode, for example, with a driving stage. All of that is possible as well. We could do that with the quad 811As, but this way, to keep it simple, we're just going to use the Class C Armstrong configuration, and we're going to tune it to the lower parallel mode. So the lower parallel mode comes out around about 2.8, 2.9 megacycles. So that means that it's a little bit off of the free resonance of this. Obviously we can load the top slightly. We could put a wire extension there or a small top load, which would bring that frequency down. But driving it in this way is more than enough to be able to show the kind of characteristics that we want to show, and makes for, as I said, a simple and straightforward Tesla coil circuit. So coming back to the wheelwork of nature, the things that we are looking for here is, particularly in this, is the frequency of free resonance. So we need to be up over about 1 to 1.2 megacycles to start to get these fractal geometric patterns. We need a positive forward pressure from the power supply. So we're going to be using the power supply with 2 series transformers, and we're going to bridge rectify that so that it's always pushing positive, and then we tune to the lower parallel resonant mode, the optimal point. In other words, as close as we can get it to the balance point without introducing instability between the lower and the upper parallel modes. Once you get to the true balance point where you've equalized the lower and the upper parallel resonant modes, then in effect your oscillator becomes unstable and can easily jump and switch between the lower and the parallel mode. So by just adjusting it down slightly, you keep it on the lower mode. If you adjust it up, you keep it on the upper mode. In this case, we develop maximum potential across the essentially quarter wave and Tesla coil by resonating it at the lower parallel mode. The only way we will be able to get a bit more out of it is to drive it directly at the fundamental series mode, but then that would require a more complex drive. Okay, so that is the setup. Now the power supply is connected out from the back directly into the top end of the primary, and we can also see, if I just move the camera around, at the back there we've got a blocking capacitor. So the output of the power supply comes to a blocking capacitor. Let me just move that into view so we can take a look at it. We're using that blocking capacitor at the output of the power supply. That's a 25 nanofarad. Oh no, we can't actually see that in the camera. Let me just put the camera down a little bit. Okay, there we are. That's a 25 nanofarad, 25 kilovolt capacitor, and that provides more than adequate for protection from kickback from the high frequency coming from the Tesla coil that might otherwise damage the semiconductors in the bridge rectifier. Normally we would make sure that that's about at least 5 times more than the size of the resonant capacitor. In this case, let's check we can see that, and we'll just come round. In that case, that's here, and also there's provision for a static capacitor. So in other words, if I want to statically use a capacitor, like this for example, so now this is a doorknob capacitor, 470 picofarad, connected to copper bars with 4mm prongs. I can use that, bridge that directly in top, and I can put a different range of primary resonant capacitors in there. I'm going to be using the vacuum variable. If I was using, let me just show, if I was using there, I could disconnect, just plug into the plastic top surface. I can disconnect the variable capacitor. So basically now I've just got the primary circuit forms a resonant circuit with the inductance of the primary coil and this statically fixed capacitor. Again, I can remove, and I'm going to reconnect vacuum variable capacitor. Okay, so I'm going to re-plug in the blocking capacitor at the back of the power supply. Let me just do that. Alright, so that's the coil unit and the coil itself, how it's set up. Now the power supply, as I said, I'm not going to say too much now about the power supply. We'll just take a quick look at it because there is a whole post on this with circuit diagrams and everything. This is nominally a 5 kilowatt plate supply, an 8-volt general HT supply. I've got the transformer configuration board set up here for 2 parallel transformers. So it's 2 industrial microwave oven transformers, 1.8 kVA each. Nominally that produces 4 kilovolts and about an amp, just over 6 kilovolts open circuit. And that's enough drive for this experiment for the GU5B. If we were going to pulse it, then we could also use we've got a 3.9 microfarad level shifter in there as well. If we put the level shifter on, we can really crank up the voltage up to over with 2 transformers. We can crank it up to about 8-9 kilovolts. And we don't need to do that in this experiment, but we could if we wanted to. The rest of the configuration, so basically you configure it here, the bridge rectifier is under here, and then it gets fed to the out. You select what output you want, whether it's a level shifter, the rectifier, or the raw output straight from the transformers. Capacitor, the blocking capacitor is connected directly across the back, and then the feed comes out there and goes directly to the primary coil. So that's as much as I'm going to say about the power supply at the moment. One other thing I wanted to show you also was just a quick check. These are very good. It's a dip meter. I think everyone in the past used to have these, but it's very good for make a quick check of your series resonance. fundamental series resonant mode. I'm going to look for where the meter reaches at some point. So around about 3.1. Yeah, about 3.1 megacycles. Okay. Okay, so that covers the system. What I'm going to do now is I'm going to set up for a run. I'm first of all going to take the camera back and just show the whole system running and the discharge. I'll bring the lights down so we can see the discharge more clearly, and then once we've seen the whole system running together, then I'm going to move the camera in closer to look at the discharge itself. We're running this in CW. I'm not running it in pulse mode. I wanted to make this first video experiment as simple and basic as possible, so not to include too many complex variables. So in other words, the results here are not a product of pulsing deliberately on the tube. Remember, we are using an SCR to power the transformers, so that will introduce a certain amount of chopping into the drive to the transformers, as they are essentially the SCR as a power controller, but we will push it up to probably full input power. For this configuration it's going to be about 2 kilowatts real power. The transformers run at a two together power factor of about 0.45 or so they'll be somewhere in about 3 to 3.5 kilowatts coming in, and about a little bit more than that, but the real power developed in the transformers will be somewhere between 1 and 2 kilowatts, depending on where we adjust it. So let me first set the camera back into a position where we can see the whole experiment. Yeah, that's it. We can get everything in, including the discharge. And I just need to connect the power up. Okay, and then we can just turn the various units on. So, turn on the coil unit. I'm going to wind up the filament current slowly up to 20 amps, and obviously it's cold, so I'm not going to just wind it fully up. I'm going to let it warm up slowly. It's a large tube. If I just had the variac set where it would be nominally, and turned it on, there'd be a very large inrush current. We don't really want to do that. We reduce the lifetime of the filament. Okay, up 20, it falls away. We're winding it up until the voltage reaches nominally 12.6 or 12.5 is really as accurate as we can measure on the meters that we're using. Back up to 20 amps again. Now to 7.5 volts. $10 volts, just over 20 amps. And finally up to 12.5. Between 23 and 24 amps being consumed by the heater, and we're just going to let that warm up for a bit. In the meantime, I'll just turn this on, so the low tension's on, the high voltage is on, the power screen is also on, and that's a complete power unit in one. It shows voltage, current and real power factor all together, particularly useful. Okay, we'll just have a final check. Make sure everything's connected correctly. Using the rectifier. The rectifier is set here. Blocking capacitor's connected and the high tension is connected as well. We've got two transformers selected. We set it to SCR, so SCR input, and we are basically using a remote control, so we don't have to get close to the system when we're running it. And I'm going to bring the lights down. Okay, so there's the lights down. You can see everything's up. And we'll wind up slowly. And we can see the image first of all. It's low tension. Just check it's coming out on the image. That's 1.8 kilowatts. Let's just see if we can. So we're running at 1.8 kilowatts CW, and we can see the structure and nature of the discharge. Okay, so that shows how it all operates together. We're consuming about 13 amps, real 17.2, obviously it's apparent power is different. Power factor 0.47 in CW. Okay, give the system a little bit of a chance to rest, and I'm going to move the. Now I've seen everything working together. I'm going to move the camera into close proximity or closer proximity to the discharge, so we can actually look at the discharge itself. Okay, so I've moved the camera in closer. What we can see in the bottom is just the tip coming off with a high voltage. So right in the bottom there's the high voltage standoff, and then it come up to that probe tip, which is basically a copper, a short length of copper into a mount into the 4mm post. Okay, so I'm going to wind up the power supply again, slowly. So there's the beginning of the breakout. Bringing it up more and more. 400 watts. Kilowatt, 1.6, 1.85. Just look at the structure and form of that discharge, the fern discharge, fractal-like. Going to measure some of those as well in the write-up. We're going to be looking for the golden ratio proportions in that as well. Nice and stable. Only in CW, no pulse going on here. Just bring it slightly down. Oh no, that's not focused. It's better. So we just get the beginning of that main central fork. Very hot discharges, a lot of current in the discharge. This is now wound down to about 400 watts. Even less, just at the start of the emanation of that. I'm just going to give it a little break, and then I'm going to wind it out very slowly again. Okay. Just check the temperature. The primary is hot to the touch. That's the product of running it in CW. Obviously in pulse mode we'll be able to reduce some of that, but I want to not use pulse mode. Pulse mode can be produced several ways. The most common way in this kind of configuration is to put a synchronized SCR with the line supply into the cathode side of the tube, so cathode down to the earth connection, and then you control the on point of the SCR and the phasing, and that gives you a form of pulse performance or switched performance. Okay, let's wind up again and get it so it just starts coming out. Develop it a little bit. 200 watts. Now it starts developing into the fern. So here it's just starting to emanate. Now it really starts to develop those tendrils. Watts. Take it down slightly. So the fern type tendrils with the orthogonal tendrils coming off them, the curve of those tendrils we're going to measure for the golden ratio. It's a self-repeating, self-similar fractal type structure. Orthogonal emanations. Lots of power now. 1.8, 1.9 kilowatts. Very hot, white. Lots of secondary and tertiary tendrils showing the same repeated self-similar fractal-like nature. Wind it down a little bit, back down, just at the beginning of those emanations of those tendrils. And we'll just let the system have a pause, let the primary cool down a little bit, and then we'll have another run. Okay, so I've given the system a little bit of a rest, a chance for mainly the primary to cool down. Transformers and the power supply are barely even warm. So we're going to wind up slowly again, looking at the structure and geometry of this fractal fern discharge. Okay, we're just breaking out, just under 200 watts. $250. Not really seeing much of the fern structure yet. Got to go up, got to push it harder. 300. Okay, now we start to see some of that, and we also notice a change in the sound. Before it was harsher, now it's become more steady. Just hold it there, about 360 watts, right at the beginning. Up in power, start to see more bifurcation, start to see the proper development of those primary tendrils. see the secondary and even tertiary tendrils in some cases. Self-similar like structure, fractal type structure. The orthogonal nature of each of the secondary and tertiary. Now we're up to 500 watts. Fully developed. That whole structure is about 25 centimeters high, 20 to sometimes 20 to 30 centimeters high from the tip upwards. 1.9 kilowatts now. Very well developed, very strong. All in CW. It's about a kilowatt. Fine detail, very fine nature will come out on the photographs. The tiny fronds, displacement like fronds that go into the tendrils. Very good. Nice and stable. GU5B has no problem pushing this. Now as the power supply we're running at 1.85 kilowatts. Wind back down. And off. Give the system a bit of a cool down again. Just check the temperature. Yeah, so the primary is hot. Not surprising. Okay, so let me bring the camera back out again. We'll just have a summary, bring it right out so we can see the experiment. Refocused. Okay, there we go. So I'm going to do one so we can see everything together. I'm going to do one last run video before I take some pictures. Okay, so we wind up. There's the emanation. Fern's already quite well developed, 360 watts. See the size of the discharge in relation to the coil. 400 watts. Fern very well developed. 600, 700, 1.7 kilowatts. 1.9. Fully developed. Very smooth. Very smooth running indeed. Nice and stable, lots of structure detail. Very interesting geometric discharge. Fractal fern-like discharge. With primary, secondary, tertiary filaments. Running at 1.9 kilowatts stably. Okay, good. Wind back down. Start of where it starts to become a fern. About there, starting to get fern-like structure. And then off. Very good. Right. Well, we'll just move this in a little bit again. Okay, so that was really the video experiment for the first in the series of the Wheelwork of Nature. Fractal fern discharge. First demonstrated, to my knowledge, by Eric Dollard back in the 90s with his very famous picture. And we saw from the discharge itself, we can see the type of structure that we've got there. So when it developed into a fern, you have a fractal-like, self-repeating, self-similar type structure, going from the larger to the smaller. So as you go through the primary tendril to the secondary tendril, even to the tertiary tendril, each of them takes on the same geometric. It comes out orthogonal from the previous tendril, and then grows outwards in this fern-like, fractal fern-like structure. We're going to do some analysis on some of the pictures of this, so we can see if the golden ratio proportion fits those tendril curves. It looks to me very much like part of the golden spiral. There we're going to see how closely that actually fits both the squares proportion model and the pure spiral is logarithmic, but the golden ratio squares proportion model gives a very, very close approximation to the golden spiral, and we're going to see how that fits to the tendrils, what the fit is like. We also can look at the fine detail, the orthogonal emanation of subtendrils, and also the very fine detail, which we may not see on the video but will come out in the pictures, of the very, very fine filaments. And those very fine filaments in the tendrils are also one of the smallest but one of the most important details. Those are indicative of displacement. They have analogies and correspondences to the kind of tendrils that Tesla observed on the railway line and reported by Oscillator in his famous book on the secrets of Cold War technology. And those very fine filaments there, I conjecture are the product of a displacement event taking place on the tendrils, and I'll develop a little bit more on that in the write-up. So that was the first experiment on the Wheelwork of Nature, the fractal fern discharge. Great, very good.